All right, now we're going to look at graphing polynomials. So this one kind of takes you through all the steps, and then we'll do another one where I'm just asking you to make the graph without analyzing every little piece. So this talks about using the leading coefficient test to determine the end behavior. So to get the end behavior, you need to think about what would happen if you multiplied out the factored form here. So you don't really need to do it, but you need to multiply all the beginning parts. So that would be negative 3x to the 1, 2, 3, 4, 5, 6. Okay, and then there'd be plus a whole bunch of other things. But what that tells you is this polynomial is going to open down at the ends. So now you have to look through the list, and the one that works is the graph falls to the left and falls to the right. Okay, and we'll see how that affects us when we graph in a minute. Okay. All right, then part B asked you for the x-intercepts. That's the same as the zeros of the polynomial. Okay, that's what they mean by zeros or roots. Okay, that's what you did algebraically in the previous video. All right, love having the factored form. Makes it a piece of cake to find the zeros. Because from this x, we know 0 would cause everything to be 0. From this one, we can see 3, and from this one, we can see negative 5. So those are the zeros. All right, this question also goes on to ask you what the behavior is going to be like at those zeros. That has to do with multiplicity, with the exponent on those. So that's the exponent on the factor. Okay, so 0 has multiplicity 3. The 3 corresponds to that factor. It has multiplicity 2. This one has an understood 1. So this is going to behave like a cubic. This is going to be like a parabola. And this is going to behave like a line. Okay, so then when you go back to fill in, it says, at which zeros does the graph of the function cross the x-axis? Crosses x-axis at both 1 and 3. No, I said that wrong. That's not what I meant to say. I'm just tired. Okay, crosses the x-axis at 0 and negative 5. Okay, because the multiplicity is 1 and 3 is odd. Okay, and then the next part says at which 0 does the graph touch and turn? Touch x-axis and turns at 3. Okay. And it says on C, they want the y-intercept. Okay, so that's what happens when you plug in a 0 for the x. And so we have to go all the way back, but because there's an x out in front of everything, it's going to go through the origin. Okay, so this is the original function. If I put a 0 in, it for all these x's, it doesn't really matter here at the end. Because when I put that 0 in, this right here would be 0 times something, so that's going to be 0. Okay, so that means the y is 0. So the y-intercept is actually the origin. Okay, and then now we're finally getting around to graphing it. So that's where we put everything together when we think about the graph. So we had it having 3 zeros, 0, 3, and negative 5. So you know it's going to have a point on the x-axis at those locations. And then you know how it behaves at each of those. So you know at 3 it behaves like a parabola, at 0 it plays like a cubic, and at negative 5 it behaves like a line. What you got to do is put that together with the very first question, which was end behavior. Falls to the left, falls to the right, should look like that. Okay, so I'm going to start from down here. I'm going to go towards negative 5. I'm going to think about my behavior at negative 5. I'm going to cross the x-axis nice and smoothly. Then I'm going to come around And when I try to hit 0, okay, 0 had a cube, so I'm going to come a little bit to the left of it so I can flatten a little bit before I cross. So it still just crosses right there. That's kind of an inflection point, it's called. Then I'm going to turn around. When I hit 3, since the exponent was 2, it had multiplicity 2, which meant it's going to behave like a parabola right there. It's going to touch and turn. And then see how the end behavior ultimately is pointing down on both ends? There you have it, okay? All right, and then let's go back and look at one where we don't analyze it in such a gory detail. Number 36. 36 just asked you, okay, f of x equals, and it gave you the factored form of this parabola. So you want to think about the leading term. It would be x times x times x to the second. It would be x to the fourth. So ultimately, it's going to open up. It's going to have a bunch of other terms here, but I don't care about them. This tells me it's going to ultimately open up. Okay, now I'm going to pull the zeros out of each of these. So those are the zeros, and I'm going to consider their exponents. The multiplicity, understood 1, and a 2. Line behaves like a line, behaves like a parabola. Okay, so you come in and you put all that together. So you're going to have it crossing at 5, at positive 3, and at positive 2. So kind of jammed in together. I think I'm going to redraw that so they're more spread out. Okay, so let me fix that a little bit. We stretch out that side of it and spread these out just a little. So it's going to cross it, or it's going to have an x-intercept at 5, at 3, at 2. Starting from above, because of the end behavior, when I get to 2, I have to bounce because it's supposed to behave like a parabola. Then I have to go through smoothly at 3, go through smoothly at 5, because they have to behave like a line. So there's no flattening or anything. And that should be your picture. Okay. All right, let me go ahead and squeeze in the one that goes the reverse of this. So let's look at number 38. 38 gives you some information about your polynomial, and you're the one who has to come up with the equation. So it tells you the 0, it has a 0 of 0, and it tells you you have a 0 of 4 with multiplicity 2, okay? And then the other piece of information that gives you is that f of 5 is 20. We'll use that near the end. So first you say, okay, I have these two zeros. That's going to give me the factor x minus 0, or really just x. This gives me the factor x minus 4, okay? Now, the 0 didn't have a multiplicity listed, so it's understood 1. This one was multiplicity 2, so that tells you the exponent you're going to have on that factor, okay? All right, let me put that back where it's supposed to be. Okay. Oops. All right, and that's little times right there. So basically, you've got a polynomial that passes through 0, that has zeros at 0 and 4 with multiplicity 2. Okay. But there's a million of them, infinitely many of them, and I need to pinpoint which one makes the polynomial pass through that point. So I'm going to plug a 5 in everywhere there is an x. So I'm trying to find the a value. Oops, I want that to be 5 minus 4. I want this black. Okay, so plug in the 5 everywhere there is an x, and you want to know where does that wind up being 20. Okay, so this is a times 5 times 1 squared, which is just 5a is 20. So a would have to be 4. Okay, and that's not because I divided by 5. Don't misuse your function notation. That's wrong thinking. Okay, so you're going to come up here and put in the 4 for the a. Then you have your x and your x minus 4. And that's your polynomial right there. Okay. All right, so it said to find a polynomial of degree 3 with real coefficients that satisfies the following conditions. basically you got it. It's just to prove that it's real coefficients, you actually have to multiply it out. But I'd give you partial credit because this is just kind of tedious. That would ultimately be minus 8x plus 16. Once you FOIL it and combine your like terms, so it's 4x to the third minus 32x squared plus 64x. Okay, and that's what they want on number 38. So that's kind of the end of the polynomial unit. And then there's a little section on rational functions. So I'm going to work on that tomorrow in class, and I'll also post a video after we do that. So let me stop where I am here.